Hello students, welcome back to the classroom point. In our today's class, we are going to discuss about the polarity in the covalent bonds as well as the dipole moment and its respective examples. So we shall begin the class now. Or else simply we can say that polarity in the covalent bonds. So let us see what is the definition of the covalent bond for a while. We know that the bond formed by mutual sharing of electrons is called the covalent bond. So that if you imagine there are two atoms, hydrogen atoms, each hydrogen has to contribute one electron for the bond formation with opposite spin. Later these two electrons come between the both of these hydrogens, so that these electrons must be equally shared by both of these hydrogen atoms, and it is shown by a single bond. So like this the covalent bond is going to be formed. But here the bond is formed between the same atoms. What happens if the bond is formed between the two dissimilar atoms? So based on the type of atoms involved in the formation of the covalent bond, these covalent bonds are categorized into two types. They are non-polar covalent bonds and polar covalent bonds. So let us see the non-polar covalent bonds. Usually these bonds are formed. These covalent bonds are formed between the similar atoms. Or we can say that identical atoms. Example, bond between the two hydrogens in H2 molecule, bond between the two fluorine atoms in the F2 molecule, bond between the two chlorine atoms in Cl2 molecule, bond between the two iodine atoms in the iodine molecule, bond between the two bromine atoms in the bromine molecule, and bond between the two oxygen atoms, and bond between the two nitrogen atoms, etc. So if the bond is formed between the same atoms or identical atoms, then the electronegativity of the both of these atoms is same. Hence, bonded electrons cannot move towards any of the direction. Hence, these bonded electrons are equally shared between the both of the bonded atoms. Hence, these type of the bonds are considered to be non-polar in nature. But remember that no covalent bond is 100% non-polar in nature. There shall be some ionic nature in every covalent bond. For example, if you consider the H2 molecule, it is the bond formed between the identical atoms, even though there must be some ionic character in this covalent bond. So that no covalent bond is 100% is covalent in nature, there shall be some ionic in nature. But usually we consider the bond forms between the two identical atoms is a non-polar covalent bond. The reason for this some ionic nature is it's a momentary ionic charges. Means at any given of the time, if unsymmetrical distribution of the electrons are present on either of the atoms, then there shall be some changes in the bond electrons movements, so that they go to the atom that has the higher positive charge, means which has the more power to withdraw the electrons, and which has the less power to withdraw the electron, that side it will less electron density will be present. That creates the momentary ionic character to the covalent bonds. Now, what happens if the covalent bond is formed between the dissimilar atoms? So, polar covalent bonds, these are formed between atoms of different elements. So when the bond is formed between the atoms of different elements in the sense they will have the different electronegative character also, then automatically electronegative difference arises that creates the movement of the electrons. Let us see an example. If we take hydrofluoric acid or hydrogen fluoride molecule, so this hydrogen fluoride molecule is formed by equal contribution of the electrons from both of these atoms. Hydrogen is contributing one electron and fluorine also contributing one electron for the bond formation. Even though both of these atoms are contributing for this bond formation, the electron density more likely to arranged close to the fluorine atom than the hydrogen atom. The reason is fluorine has the highest electronegative character. That means pulling capacity of the bond electrons towards its side is more for the fluorine. That is the reason why most of the bonded electron density is located closer to the fluorine, which gives partial negative charge to the fluorine. Since hydrogen is losing bonded electron density towards the fluorine, it gets partial positive charge. So because of the electronegativity difference, electrons in the bonded bond are not equally located. They are not they are not in the equal distance. They are located closer to the one atom and away from the one atom. That creates the negative pole and a positive pole. These two are called the dipoles. And here these dipoles shows that the movement of the electrons, you can see that the flow of electrons from the less electronegative atom to the more electronegative atom is shown by the cross tail arrow mark pointing the arrow towards the more electronegative atom, whereas the cross tail is towards the less electronegative atom that gets the partial positive charge. So basically this type of arrow mark shows the movement of the electrons or flowing direction of the electrons. So this type of means how much negative charge is created, how much positive charge is created, in which direction electrons are going, and all these shall be discussed by the concept of dipole moment. So we shall begin the concept of the dipole moment. Dipole moment. It is denoted by the symbol mu. So dipole moment can be defined as it is the product of charge on the atoms and distance of separation of the charge. So this charge on the atoms is represented by, we can say that mu equals to charge. Charge is represented by the letter Q, that is quantity of the electricity in the coulombs, into distance of separation. So now dipole moment is the cumulative effect of the charge and distance. When charge quantity increases, dipole moment increases, saying that radial distance is same. If distance increases, then dipole moment also increases. There are some cases where charge is more, distance is less, or distance is more, charge is less. Those cases we shall see, and how to calculate the dipole moment for such type of the molecules. And the units of the dipole moment equals to, usually we calculate these are in the dBi units. 1 dBi is equals to 3.33546 into 10 power minus 30 coulomb meters. This is in SI units, or else 10 power minus 18 electrostatic units centimeters. These are in the CGS units. And we must remember one more thing, that dipole moment is a vector quantity. The reason is it has both direction and magnitude of the charges. That's why dipole moment is considered as the vector quantity. Now the question arises, in case of the multi-atomic molecules, the dipole moment, if two different bonds are having the dipole moment, then how to calculate the resultant dipole moment? So let us take there is an atom X which is connected to the two atoms Y and Z. Imagine the electronegativity of the Y is more than X, so that the flow of electrons are towards the Y, which gives partial negative charge to the Y and partial positive charge to the X. And also Z electronegativity is also more than the X, so that the flow of electrons are towards the Z, which gives partial negative charge to the Z and partial positive charge to the X. Now let us imagine the dipole moment of the first bond is mu1, second bond is mu2. When this Z is dragging the X towards this side and Y was dragging the X towards that side, so X cannot move either this direction or this direction. The net force of the moment of the X will be in this direction. So that's why in case of the polyatomic molecules, the resultant dipole moment is the vector sum of the dipole moments of the individual bonds. So that here the direction of the X will be in this direction. This is called the resultant dipole moment. And imagine now that for calculation, let us imagine this is the theta angle. So that now resultant dipole moment can be calculated by mu1 square plus mu2 square plus 2 mu1 mu2 cos theta whole power 1 by 2, that means root. So that in this case, if theta equals to 0 degrees, then mu r is maximum. So that here we can write down that mu r is equals to mu1 plus mu2. What happens if theta equals to 180 degrees? 180 degrees in the sense they are acting opposite direction. So when they are acting opposite direction, they get cancelled out. That's why then mu r, resultant dipole moment, is minimum. And here we can write down that mu r is equals to mu1 minus mu2. So that here we can write down that resultant dipole moment is inversely proportional to the separation of the or angle of separation. Angle of separation, or simply we can say that bond angle in case of the planar molecule. So more distance the groups are going, the dipole moment gradually decrease. More closer the groups, there shall be more effective dipole moment. So let us see some examples, which molecules shows the dipole moment and which molecules do not show the dipole moment. What are the conditions required to understand the molecules showing the dipole moment as well as the molecules that don't show the dipole moment. Molecules that do not show dipole moment. These are usually called as the symmetrical molecules. All symmetrical molecules do not show the dipole moment. Let us take few examples here. The first one is BeCl2 molecule. You see there, beryllium chlorine bond is polarized because chlorine is more electronegative. So the movement of electrons in this bond is towards the chlorine and in this bond is towards this chlorine, and the net movement cancel out. That's why dipole moment of this molecule is equals to 0. And let us take carbon dioxide molecule. In this carbon dioxide, oxygen is more electronegative, carbon is less electronegative. So altogether the movement of electrons or from carbon to oxygen. Here also carbon to oxygen. Since the force of movement towards the both directions will be same, so that the carbon moment or the net moment of the electrons will be zero. That is the reason why dipole moment of this molecule is equals to 0. Let us take the BCl3 molecule. So in BCl3 molecule, we know that chlorines are more electronegative than the boron, so that the movement of electrons from boron to chlorine in every bond. So it has to show the dipole moment, but in reality it doesn't show the dipole moment. The reason is, see, this chlorine and this boron chlorine bonds are moving this direction. The resultant dipole moment arises from both of these bonds will be this direction, which is cancelled by the opposite boron chlorine bond. And from this boron chlorine and this boron chlorine bond, the net moment of the boron could be towards this direction, which is cancelled by the opposite boron chlorine bond. And the resultant dipole moment arises from this boron chlorine bond will be in this direction, which exactly cancelled by the opposite boron chlorine bond. Means in this molecule, the resultant dipole moment arised by any two boron chlorine bonds is exactly cancelled by the opposite boron chlorine bond, that is third boron chlorine bond. Hence the molecule is 0 dipole moment. You should remember one thing, that in these molecules the bonds are polar. See, bonds are polarized, but as a whole the molecule net dipole moment value is 0. That is the reason why, despite having the polar bonds, these molecules are called the non-polar molecules. Let us take the fourth example. Methane molecule. Movement of electrons are towards the carbon. All are coming to the carbon. Final cancellation will be there. Hence dipole moment equals to 0. Let us take the CCl4. In this case, the electrons are moving away from the carbon atom. So the net moment will be cancelled by, so the moment coming from the any two bonds will be cancelled by the remaining two bonds. Hence, dipole moment equals to 0. Let us take SO3 molecule, where the dipole moment again exactly cancelled by the bonds like in the BCl3 molecule. So this molecule also carrying the 0 dipole moment value. Next, let us take the PCl5 molecule. The structure of PCl5 molecule is like this. These two chlorines cancel each other. These three chlorines are in the planar shape. The net dipole moment arises from the any two phosphorus chlorine bonds in these three chlorine bonds will be cancelled by the third chlorine bond. See, the net dipole moment from these two bonds is this direction, cancelled by this one. And a net direction from this one will be this direction, cancelled by the third one. So like that, the moment coming from the any two phosphorus chlorine bonds in the equatorial bonds, the cancelled by the third phosphorus chlorine bond. Hence, dipole moment value is equals to 0 in this case. Eighth molecule, SF6 molecule, sulfur hexafluoride. See, these all bonds are opposite direction only, so that mutual cancellation gives 0 dipole moment to this molecule. chlorine, chlorine, opposite value, so dipole moment is 0. Bromine, bromine, again they are working opposite side, so dipole moment equals to 0. Cyanide, cyanide group, again in the planar shape, dipole moment equals to 0. If you take the XeO4 molecule, here also dipole moment value equals to 0 because mutual cancellation, just like a methane molecule. XeF2. When you take the XeF2, it is a linear shaped molecule which has 0 dipole moment because the dipole moment arises from the any two lone pair of electrons cancelled by the third lone pair of electron in this planar shape, and the fluorines are acting opposite side. XeF4 molecule. Here also dipole moment value equals to 0. Next, let us take the PCl3F2. Fluorines occupy the equatorial places, being the smaller atoms. Larger atoms occupy the equatorial position, so they are acting opposite direction. So dipole moment value equals to 0. Trans configuration. So all trans molecules are not having the 0 dipole moment. Reason here is trans configuration means any two groups, if any two identical groups on the double bond are opposite direction, then that is called the trans configuration. So if these two groups are in the opposite direction, it is a trans, but that is not the case here. In the trans molecules, each carbon atom must have the identical groups. Here CH3 hydrogen there, here also CH3 hydrogen must be there. In such cases only the opposite cancellation will be there, so that dipole moment value is equals to 0. Now let us use few more molecules where dipole moment values are 0. So in this case dipole moment is 0 because the net moment will be in this direction, cancelled by the third chlorine bond. From these two bonds, net direction will be in this direction, cancelled by the third bond. And from these two chlorines, net direction will be this direction, cancelled by the third bond. And 18 IF7 molecule is also having the 0 dipole moment. So these are the some molecules with a 0 dipole moment value. Now let us see the other molecules which are having the dipole moment. Unsymmetrical molecules, and these are also known as the polar molecules. Let us take few examples here. Hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. See these bonds where halogen atom gets the partial negative charge. In all these molecules, hydrogen gets the partial positive charge due to the difference in electronegativities. That's why Here the bond movement of electrons towards the halogen atom, here also like that only. So in all these cases, flow of electrons are towards the halogen atom. But the question arises, among these which is having the highest dipole moment value? So dipole moment value basically is the product of the charge and distance of separation. So here charge is more for the fluorine being a more electronegative element. It grabs the most of the electron density towards its side. So the partial negative charge density gradually decreases from fluorine to the iodine. So that the Q value gradually decreases. But fluorine to the iodine atomic size increases, so the distance of separation increases. Even though distance of separation increases, the quantity or the magnitude of the charge that created on the fluorine is outperforms all these values, so that its value is higher than the product of the charge and distance of any of these molecules. That's why the dipole moment of HF is greater than the HCl, which is greater than the HBr, which is greater than the hydroiodic acid. Now let us take this similar example. CH3F CH3Cl, CH3F, CH3Br and CH3I. In these cases also, halogens attains the partial negative charge, whereas carbon attains the partial positive charge. So again, if you consider only electronegativity, then these also must have followed this order, but it is not being done. The reason here is, in case of the methyl halides, carbon is not like hydrogen. Carbon has higher electronegativity than the hydrogen. That's why the electron density lost by the carbon to the any halogen atom is less. So hence the quantity of the negative charge developed on the fluorine in this case is less than the HF molecule. So, but if you take the chlorine atom, it has the even lesser electronegativity or lesser electron density on it than the fluorine, but here the larger atomic size. So the cumulative effect of the charge and distance of separation is more for the methyl chloride than methyl fluoride. Then the question arises, then these are having even more, this means more size than the fluorine atom. Why these are not having the higher dipole moment more than methyl fluoride? The reason here is, these are having the larger atomic sizes and larger distance of separation, but the magnitude of charge developed on their atoms is very less, so the cumulative effect is less, hence they are having the less dipole moment value than the methyl fluoride. Now let us take another example. So in the case of methyl chloride, the arrangement of bonds is like this. In the case of the dichloromethane, the arrangement of bonds is like this. And chloroform like this, and carbon tetrachloride is like this. So among all these cases, carbon tetrachloride is having the symmetrical tetrahedral structure without lone pair of electrons, so its dipole moment value equals to 0. But what about these cases? Here electrons are flowing from the 3 carbon hydrogen bonds towards the carbon, and chlorine is taking the electrons. So there is a net movement of the electrons towards this side. So that's why methyl chloride has the higher dipole moment. And in this case, See, this chlorine is dragging the electron this side, but this is doing in the opposite direction. And here it is giving electrons, and here also it is giving electrons. So the giving electrons process is less than the taking of electrons process, because chlorine is more electronegative. That's why chlorine is withdrawing the more electron density than the electron density given by hydrogen to the carbon. That's why there shall be not exactly cancellation, but still dipole moment arises. That's why CH2Cl2 has the higher dipole moment than this molecule, but lower than this one. And in this case, see, 3 chlorine atoms are dragging and 1 hydrogen is giving. And do not misunderstand that the moment is this direction. Why? Because this is a tetrahedral shape, not the pyramidal shape. So all bonds are in the equal distance with equal directions. That is the reason why these 2 bonds cancel each other. This is giving, this is taking to some extent. That's why chloroform is having some dipole moment, whereas CCl4 is having the completely 0 dipole moment value. Let us take the NH3 versus NF3 molecule. So both are pyramidal in shape, but in case of ammonia, the electrons are moving towards nitrogen from 3 nitrogen-hydrogen bonds. Wherever lone pair of electrons are there, lone pair never give electrons to the central atom, they always take the electrons. So that here the electrons are moving towards the lone pair of electrons. So these 3 bonds are giving electrons to the nitrogen, and lone pair of electron also taking the electron that direction. So final movement, resultant movement of the electrons will be in the upper direction, so that it has the higher dipole moment. It is an additive property. You can see that these are added to the moment of lone pair of electrons, so that's a final movement will be this direction. But in this case, fluorines being more electronegative, they drag the electrons, but lone pair is doing work opposite direction. But this lone pair cannot exactly cancel the force coming by the 3 nitrogen fluorine bonds, because these are strong electronegative atoms, so they exert the more force towards the downside than this one. But anyhow, these 2 forces are working opposite direction. This cancels, the lone pair of electrons cancels somewhat the force arised by the 3 nitrogen fluorine bonds, so that here the net force will be this direction, but that net force is somewhat cancelled by the lone pair of electrons. Hence, ammonia is having the higher dipole moment than the NF3 molecule. Next example, H2O. So in this case, electrons movement is towards the oxygen side, which is more electronegative, and these electrons are taking this side. So there shall be net force of the movement, resultant dipole moment towards the upper side, so that H2O is having the dipole moment value. And in the similar way, H2S also having the dipole moment value, but between H2O and H2S, the dipole moment in H2O is more than the H2S, because of the more electronegative nature, more charges shall be created on the oxygen than the sulfur. So oxygen is having the smaller size, larger negative charge. Sulfur is having the larger size but small negative charge. That's why cumulative effect is more in the case of the H2O than the H2S. Now the question arises that HF molecule, NH3 molecule, H2O molecule, which is having the higher dipole moment. See that here 4 forces are working in the same direction. And moreover, oxygen is second most electronegative element. That's why the dipole moment of the H2O is always greater. Now, these two cases, if you understand, nitrogen, here also 4 forces are working, but the question is, nitrogen is a larger atom and having the lower electronegativity than the fluorine atom. That is the reason why the magnitude of the charge created on the fluorine is more. Hence, it has the higher dipole moment than the ammonia. And their boiling point values also follows the same order. Boiling point as well as dipole moment. Let us see a few more examples. Next example is orthodichlorobenzene, metadichlorobenzene, and paradichlorobenzene. I already told you, in case of planar molecules, dipole moment is inversely proportional to the angle of separation or bond angle. So here separation is only this much, here more is there, here even more is there. Here net force will be this direction, here net force will be this direction, here net force cancel out. Zero dipole moment. So dipole moment order is like this. When two OH groups are in the opposite direction, dipole moment not equals to 0. The reason for this is so they are not acting exactly opposite direction because here lone pair of electrons are there. So this area will create separately dipole moment values. That's why dipole moment value is not equals to 0. And similarly, SH molecule also dipole moment not equals to 0. If different atoms are in the opposite direction, then moments are not exactly cancelled, so that dipole moment value is not equals to 0. We must remember that the dipole moment of this molecule is closely equals to the dipole moment of this molecule. Reason is here only one chlorine atom is there, so that expect dipole moment. So in this case, these two chlorines resultant dipole moment will be this direction, cancelled by the third chlorine bond. And these two chlorine bonds moment will be this direction, cancelled by this bond. And these two chlorines will be this direction, cancelled by this bond. So what is left behind is exactly the bond is coming by this bond. So the dipole moment arises from this bond is the final one, which is not being equals to 0. That's why both of these are having the equal dipole moment values. SO2 molecule, it is having the dipole moment value. So in this case, dipole moment value not equals to 0. Even carbon monoxide has the dipole moment, whose dipole moment value not equals to 0. And when you take this molecule, bromobenzene and bromocyclohexane, in case of the bromobenzene, what happens here is because of its minus I effect, the electrons flow will be this direction, and because of its conjugation, the electrons flow will be this direction. That means both of these forces are acting opposite directions, not only bromine, any of these halogens. But minus I effect is stronger than the its plus M effect. That's why it has the resultant dipole moment in this direction. But these are having the weak dipole moment values because their own plus M effect is cancelling the moment of the flow of electrons arises by the minus I effect. But in this case, such type of effect is not there. Hence, dipole moment value will be in this direction and having the higher dipole moment value. Now, let us take the cis molecules. Cis molecules always possess some dipole moment value, so their dipole moment value is not equals to 0. XeO3 so unsymmetrical, hence dipole moment value not equals to 0. If you take PCl3, not equals to 0. PF3, dipole moment not equals to 0. So I'll take one more example here. PCl2F3. So when you take this molecule, larger chlorine atoms occupy the equatorial positions, smaller fluorines occupy the axial positions to minimize the repulsions, and one more fluorine is here. That is the reason why the net dipole moment arises from the phosphorus chlorine bonds will be this direction, not exactly cancelled by the phosphorus fluorine bond. Anyhow, these two bonds will get cancelled out. That's why this molecule still possessing dipole moment, so that we can call these all molecules as polar molecules. Dear students, I hope you understand my class about the dipole moment. If you really understand this class, do like my videos and share it with your friends. Thank you one and all. We shall meet in the next class.